Great. So thank you for coming along to this first talk after the break at PyCon 2017. Our presenter is Kavya Joshi, who is going to be telling us about the Memory Chronicles, A Tale of Two Pythons. Please make her welcome.
Good morning. How's everybody doing today? Sufficiently caffeinated for a talk on memory? My name is Kavya, and today I'm here to talk about the memory use in Python, specifically why and how different flavors of Python, different implementations, have vastly different memory profiles. So first things first, what do I mean by different flavors or implementations of Python? These are simply different implementations of the Python language spec, right? Ones that we've all heard of are CPython, which is the standard, the default implementation, the Python that we all use and love. Unfortunately, CPython has somewhat of a bad rep when it comes to its memory use, right? Actually, how many people here have personally been baffled by or wondered why their Python program was using so much memory? That's a lot of hands. That's about everybody. There are other Python implementations. There's PyPy, there's IronPython, and there's one that we're specifically interested in today, and one that's specifically interesting to our discussion of memory use, MicroPython. Anybody here use MicroPython? MicroPython is the leanest, the meanest, smallest Python implementation. It's intended for use in microcontrollers, right? So you can control hardware using Python, and that's neat. But what's even neater is that it runs on microcontrollers, right? These are highly constrained systems. We're talking 16 kilobytes of RAM, or about how much space it takes to store that top left picture. Now, MicroPython is a Python implementation. It implements the Python 3 spec, but it should be noted that it's not a full implementation, right? It doesn't implement certain parts of the specification. It implements most of the standard library, but not all of it. And the reason for this is it's intended for use in microcontrollers, and some of that functionality doesn't make sense for, and it's unsuitable for these constrained systems. Examples are metaclasses, multiprocessing. It has minimal multi-threading support, but these are things that it just doesn't need, and it would be a bad idea to implement. All right. So CPython and MicroPython are the two Python implementations we're going to talk about today. So the question is, why did I pick these two? Well, it turns out they're actually fairly similar under the hood with respect to the machinery, with respect to how they operate, right? They're both bytecode interpreters, so the Python source is compiled down to bytecode, and that is what's evaluated. They're both stack-based virtual machines. If you don't know what these words mean, it doesn't matter. The idea is the interpreter pushes and pops values of a value stack. And finally, they're both C programs. So they're fairly similar. And yet, despite that, they're practically on opposite ends of the memory use spectrum. But you don't have to take my word for it. Let's look at some numbers. So first things first, these are the specs of the laptop that these experiments were run on. What matters is it's a 64-bit. I was running Python 3.6, and MicroPython has a Unix port, which is why I could run it on my Ubuntu box. The methodology used for these experiments, these are not formal benchmarks by any means. These are just simple experiments. I created a number of objects of the desired type in a loop, so up to 200,000 of them. And I measured memory use from within the Python process, so using utilities such as sys and the memory profiler for CPython, and the MicroPython and GC modules for MicroPython. It's also important to note that I measured heap use. Heap use is what we care about for this talk. For those of you who might have forgotten your computer architecture class, a process's memory is divided into the stack, which is usually grown automatically, and the process doesn't typically directly manage it. And then there's the heap. Processes usually start out with a fixed amount of heap, and they grow it. They can grow it, and they typically manage it. Now, with respect to how CPython and MicroPython manage memory, they both implement custom allocators. Again, the details don't matter right now, but what's important is that CPython's custom allocator grows the heap on demand. So as the interpreter needs more memory, it asks the operating system for more memory, whereas MicroPython starts out with a fixed amount of heap, and the heap is never grown. And this, again, comes down to the fact that it's intended for microcontroller systems. Okay, so that's what we're measuring. We care about heap usage. So this is what the graph looks like for integers. The numbers, the exact numbers, don't matter a whole lot. What matters is the shape of those lines, right? MicroPython's is nice and flat, and CPython's solidly trends upwards. Strings looks the same. And lists. Lists look more similar, but they have the strange step function, which is also interesting. So that is the question we're going to try and answer today, right? Why do CPython and MicroPython have such vastly different memory footprints and memory profiles? And to do that, I will first talk about how they implement objects internally. I will then talk about how they manage memory and what the overhead of that is. And finally, we'll take a step back and evaluate why they do things the way they do and what the trade-offs they make are. Okay. So we've established that CPython and MicroPython have very different footprints. So the obvious first set of questions is, well, they must both create objects because Python is an object-oriented language, but are those objects they create different under the hood? Does CPython create larger objects? Does it create more objects than MicroPython? And to do that, we're going to take a deep dive into how they implement objects. First up, CPython. So CPython, it allocates and stores all objects on the heap. So for example, when you do x is equal to 1, an object with the value 1 is created on the heap, and the name x is bound to it in some namespace, in the current namespace, rather. What do these objects look like? Well, all of these objects have a common header that stores metadata about the object, and this header contains the ref count, the reference count. This comes down to how Python manages memory, and we'll come back to it. And it contains information about the type of the object. Now remember, Python is a dynamically typed language, so the objects need to hold on to their type information themselves, which is why we have that type pointer. So for example, an integer object and a list object, they'd both have these headers, and then the rest of the object are object-specific fields. Why do we care about this? Overhead. This header takes up space, right? In this case, the ref count is a C size t, which takes up 8 bytes on a 64-bit. And the pointer to the type object, it's a pointer on a 64-bit, so that's another 8 bytes for a total of 16 bytes. And this is just the overhead, right? We haven't talked about the fields used to store the values themselves. Another good reason to care about this is it gives us a lower bound on the size of the smallest CPython object. A CPython object cannot be smaller than 16 bytes. And if it needs to contain any value, which most objects do, it's going to be greater than 16 bytes. Okay, so what do these object-specific fields look like, right? So in the case of an integer, in the case of our x is equal to 1, it stores the value of the integer as an array of digits. So it contains the array, and it also has the length of that array of digits. So if we were to consider everything else except the value as overhead, the overhead of storing a Python integer, or the Python integer 1, is 16 plus 4. That's a whole 24 bytes, and then finally the value, right? We can verify this using the sys module, right? 28 bytes sounds like a lot of bytes, so let's make sure it makes sense. And sys tells us the same thing. What about a bigger int? What about x is equal to 10 to the power 10, which is the value I started with in my experiment, in my loop iteration? Well, it turns out those digits that we talked about, they're basically unsigned integers. See unsigned integers, so that's 4 bytes of 32 bits. But for some good but complicated reason, only 30 of those bytes are used to store a value. So the maximum value of one of those digits is 2 to the 30 minus 1, right? And 10 to the 10 is greater than that number. So we end up using 2 digits. So the total size of that integer is 32 bytes. And again, we can use the sys module to make sure this all makes sense. So does this graph, can we explain this graph? Does it make sense? Well, yes, it does. I created about 200,000 integers that took about 32 bytes. So we get about 6 megabytes. So that took about 6 megabytes. So that's cool. We sort of understand what CPython's doing, but that's only one half of the story. What about the other half of the story? What's going on here? What's going on with MicroPython's nice flat line? To do that, let's talk about MicroPython's object model. In MicroPython, an object is 8 bytes. 8 bytes. How does it do it? It uses a neat technique called pointer tagging, where it stores a tag, which is information about a pointer, in the unused bits of a pointer. Okay? This makes more sense if you think about it backwards, so let's do that. Most modern computers use word address memory, right? So it means that all addresses are spaced about 8 bytes apart. So pointer values will be multiples of 8. So they can be 8, they can be 16, they can be 24, but they can't be 7 or 3. Notice anything? The coloring might give it away. But the lower three bits will always be 0, right? And this comes from the fact that they are multiples of 8. And the idea behind pointer tagging is you store information about the remaining 61 bits in those last 3 bits. What do you store? What does your tag look like? You can come up with any tagging scheme, right? You can say, so you have 0 to 2 to the 3 minus 1, which is 0 to 7 values your tag can take on, and you can come up with any scheme. You can assign any meaning you like. So what does MicroPython do? Well, MicroPython does something even more clever. It says that if the last bit of my pointer is 1, it's not even a pointer, it's not even an address, it's actually a small integer. Similarly, they do something clever with special strings that we will not be talking about today. And finally, if the last 2 bits is 0, then it's actually a pointer, and it points to a concrete object. A concrete object is everything else except the small integers and these special strings, right? So lists, etc., are concrete objects. So this is neat. This means that small integers take 8 bytes. 8 bytes compared to CPython's 28 bytes. And it also means that they are stored on the stack, which is nice because it has performance benefits. So in the case of x is equal to 1, MicroPython checks, is it a small int? Does its value fit in 2 to the 63 minus 1? And it does, so it gets 8 bytes. And in CPython, this takes up 28 bytes. What about our x is equal to 10 to the 10? In MicroPython's case, it's still a small integer. It still fits in 61 bits. So it still takes only 8 bytes. Whereas in CPython, it took 32 bytes. Also, like we mentioned, it's stored on the stack, and what we measured was heap usage, which is why that line is flat. But even if you were to measure stack usage, which is a little more complicated to measure, even if you were to measure stack usage, there's still a huge difference in simply the number of bytes stored. All right, so that's integers. Now let's try and understand what's going on with strings, right? Why do our graphs look like that? Now, in CPython, again, we're jumping back to CPython land and looking at its object, its string object. We're going to be talking about ASCII strings only. They're stored in such an object. It has the same header. It has a number of fields. And finally, it has the value. To calculate the size of the string x is equal to calculate the size of the string a, right? We use the same calculation where we say size of the overhead is size of the struct, which comes out to 48 bytes, plus the size of the value. Now, the size of the value is the length of the string a, which is 1 byte. It's a null-terminated string. That adds another byte. And since we're talking about ASCII characters that take up 1 byte, it's 2 bytes, right? And that gives us a value of 50. If we were to use a larger string, again, we can apply the same formula to get the new value. So this is why CPython's graph trends upwards, right? Each string object being created is taking up about 60 bytes because I was creating strings up to length 10. Okay, so what about MicroPython strings? What does MicroPython do for strings? MicroPython has another clever scheme for strings. It stores small strings, defined as strings about 10 characters in length, or less than 10 characters in length. It stores them as an array, okay? And this array has a fixed overhead of 3 bytes. The specific breakdown doesn't matter, but its overhead is 3 bytes, and then again, it stores the null-terminated representation of the string. So what does this mean? When you create a string of length 1, the overhead is 3 bytes, plus another 2 bytes to store the null-terminated string, which is only 5 bytes, versus CPython's 50 bytes, that's 10 times as much. That still doesn't explain why the graph was flat, though, and that is because MicroPython stores these special strings in a pre-allocated array, okay? So, and because of how we measured memory in that case, since it was in a pre-allocated chunk of memory, and we didn't see new allocations, they weren't counted. Okay, now let's talk about the lists example. Okay, and that brings us to the subject of mutable objects, that can change their size. In CPython, it turns out these objects have an additional memory management overhead. So not just the ref count field, but another 24 bytes for this PyGC header that we'll come back to. So the total overhead just for memory management of these objects is 24 bytes plus 16 bytes, which is 40 bytes. In the case of lists, for example, the overhead is 40 bytes. It stores some additional fields which take up 16 bytes. And finally, the value in the case of a list is an array of pointers to items. Okay, so it doesn't store the items itself. Its array stores pointers to items, which is why if we again do this calculation, we see that the size of the struct is 64 bytes, the size of the pointer is 8 bytes, so an empty list is 72 bytes. But note that it does not account, using sys in such a way does not account for the size of the items themselves. So if you want to get the real size of the list, you have to add the overhead, you have to compute and add the overhead of the items yourself, or use something like PyAmpler. Okay, so that's cool. We now know how much memory lists take, but it doesn't really explain that step. So what is going on there? Well, it turns out that CPython dynamically resizes arrays on append operations. It doesn't do this on every append. It does it to amortize the costs of a resize. So for example, the jumps are the resizes, but at the resizes it over allocates, and so the line stays flat for a bit until the next resize. So what ends up happening is if you create an empty list and then append one to it, instead of taking 72 bytes, it ends up taking 96 bytes because of that over allocation. That is what my experiment did. It started with an array and appended to it. It started with a list and appended to it, which is why we saw that step function. What about MicroPython? MicroPython's lists seemed a lot smaller. That allows us to talk about MicroPython's concrete objects. MicroPython's concrete objects are very similar to CPython's objects in that they're stored on the heap and they have a header, but their header does not contain a ref count field. And this comes down to the fact that they manage memory differently, right? So all the header contains is type information, which takes up only 8 bytes compared to CPython's 16 bytes, right? It also turns out that in the case of MicroPython, mutable objects don't have any additional memory management overhead. They don't have that PyGC head, which added 24 bytes. But other than that, in the case of lists, MicroPython lists and CPython lists have practically the same structure with respect to memory use, right? The only overhead in CPython's case is that memory management overhead, which adds a good 32 bytes. Other than that, MicroPython's lists also do dynamic resizing, which is why we saw that step function for those lists as well. Okay. So with this, we can take a step back and try and answer the questions. Does CPython allocate larger objects? Well, based on these examples, it certainly looks like it, right? We saw some huge difference in those numbers. And this is generally speaking, yes. Now, when it comes to things like dictionaries and especially classes and instances in Python 3.6, the difference is less clear-cut because Python 3.6 does some very cool things. But generally speaking, yes, CPython's objects tend to be larger than MicroPython's objects. What about the second question? Does it allocate more objects? Again, generally speaking, yes, right? We're talking about objects on the heap, and we saw that MicroPython uses this really cool scheme with pointer tagging and storing small integers on the stack, right? So generally speaking, yes. Now it turns out that CPython and MicroPython both implement several optimizations to try and minimize the number of allocations, and we'll talk about it at the end if we have time. We likely won't, but ask me about it. Cool. So that said, we've answered the two questions we started out with, but I bet most of you have this burning question now, which is, what's with all of CPython's memory management overhead, right? We saw that it takes up, in the form of the ref count field and in the form of the PyGC head, it takes up a lot of space. So why is that? And that leads us to talk about the memory management schemes that CPython and MicroPython use. Now, CPython uses a scheme called reference counting. It's pretty simple. It does exactly what the name says it does. It maintains a reference count for each object, so how many objects reference it. So when an object is initially created, it has a ref count of 1. When another object points at it, its ref count is incremented. When you perform a del, the ref count is decremented. And finally, when the ref count hits 0, there are no more references to it, so it can be deallocated. It can be freed or returned back to the allocator. So that's ref counting, right? But our question remains, what about the PyGC head for mutable objects? And it turns out that ref counting doesn't always work. Here's a specific example of where it doesn't, right? If you have a mutable object and you create a reference to itself and then you delete it, you have a reference cycle. Its ref count can never go to 0. So it would never be deallocated. And that's a problem. And to fix that, CPython has a cyclic garbage collector as well. So it does have a garbage collector. This is surprising to a lot of people, but it does. Those are some details about the garbage collector. They don't matter super much. What matters is that only mutable objects are tracked by the garbage collector because only they can participate in reference cycles. What about MicroPython? MicroPython, we saw, doesn't have this reference count field. So what does it do? How does it know when to delete objects? So MicroPython's allocator is a bitmap allocator. It basically takes the heap, divides it up into blocks, or simply units of allocation, which are each 32 bytes. And it stores the state of those blocks, whether a block is in use or free. It stores that in a bitmap, which is simply another region of the heap. And it tracks each block. It tracks the state of each block with 2 bits. So in the example there, we can see that blocks 1 and 3 are in use because their corresponding bits in the bitmap are set. So in this scheme, how does del work? Well, let's see. When you create an object, its bits in the bitmap, the corresponding bits, are set. When you create another reference, nothing else happens other than the name binding. When you delete x, again, simply the name binding is removed. And when you delete y, the name binding is removed. Huh, strange. So what does this mean? When is the block deallocated? When are the bitmap bits set back to 0 and the block considered free? Well, it turns out MicroPython has a garbage collector as well. This is a different garbage collector. This is a mark and sweep collector. Again, the details don't matter, but it manages all heap allocated objects. All right. So with that, we now know how we now know the answer to our question, what's with CPython's memory management overhead? We know how that works. All right, so these are a few notes. So we've barely scratched the surface on CPython's optimizations, what it does to minimize RAM usage, but the source code is all really accessible and really clear C code. So if this interests you at all, I highly suggest checking it out. Cool. So anyway, so we've answered our 3 questions. So now we can take a step back and evaluate why MicroPython and CPython take the approaches they do, right? What are the trade-offs they make? Why do they do things the way they do? Let's talk about trade-offs first. So typically, memory use and speed tend to be traded off against each other, right? But that turns out to not be the case in MicroPython. They have this extensive benchmark suite for performance numbers, timing numbers on their website, and they come out on top with respect to CPython in most cases. There are cases in which MicroPython performs less well, cases usually involving large dictionaries. But overall, MicroPython remains performant. So what is the trade-off it makes? And it turns out to be functionality, right? So MicroPython, you can't do a lot of things with MicroPython that you can do with CPython. Like, for example, you don't have the extensive ecosystem of Python packages at your disposal. So that brings us to the next question, right? Why do they make the design decisions they do? Why are they each implemented the way they are? And it comes down to this. They're intended for very different uses. When CPython was first created back in the late 80s or early 90s, its design philosophies were different, right? They decided that they wanted simplicity of implementation and design first, and to worry about performance later. In MicroPython's case, that's exactly the opposite. MicroPython is a modern, is fairly modern, so it can borrow all these ideas from languages like Lua and JavaScript that have made certain optimizations in the past few years, and it's targeted solely at these highly constrained systems, right? These systems have certain properties. For example, they have a fixed amount of RAM available, they have a small heap, and it can take advantage of all of these, and it can do a better job at meeting those requirements. So to answer our last question of why they make the decisions they do, why are they each implemented the way they are, it comes down to the fact that they're built for very different systems. All right, with that we conclude. I hope you walk away today with an understanding of the object internals and the memory management internals of both MicroPython and CPython, and also an appreciation of the impact of those differences in design and implementation. Thank you.
Thanks, Kavya. We don't have any time for questions, unfortunately. So, yeah. Next talk begins in about 10 minutes' time. See you then.
MicroPython is the leanest, the meanest, smallest Python implementation. It's intended for use in microcontrollers, right? So you can control hardware using Python, and that's neat. But what's even neater is that it runs on microcontrollers, right? These are highly constrained systems. We're talking 16 kilobytes of RAM, or about how much space it takes to store that top left picture. Now, MicroPython is a Python implementation. It implements the Python 3 spec, but it should be noted that it's not a full implementation, right? It doesn't implement certain parts of the specification. It implements most of the standard library, but not all of it. And the reason for this is It's intended for use in microcontrollers, and such as in pops values of a value stack. And finally, they're both C programs. So they're fairly similar. And yet, despite that, they're practically on opposite ends of the memory use spectrum. But you don't have to take my word for it. Let's look at some numbers. So first things first, these are the specs of the laptop that these experiments were run on. What matters is it's a 64-bit. I was running Python 3.6, and MicroPython has a Unix port, which is why I could run it on my Ubuntu box. The methodology used for these experiments, these are not formal benchmarks by any means. These are just simple experiments. I created a number of objects of the desired type in a loop, so up to 200,000 of them. And I measured memory use for implementations of Python. These are simply different implementations of the Python language spec, right? Ones that we've all heard of are CPython, which is the standard, the default implementation, the Python that we all use and love. Unfortunately, CPython has somewhat of a bad rep when it comes to its memory use, right? Actually, how many people here have personally been baffled by or wondered why their Python program was using so much memory? That's a lot of hands. That's about everybody. There are other Python implementations. There's PyPy, there's IronPython, and there's one that we're specifically interested in today, and one that's specifically interesting to our discussion of memory use, MicroPython. Anybody here use MicroPython?
Great. So thank you for coming along to this first talk after the break at PyCon 2017. Our presenter is Kavya Joshi, who is going to be telling us about the Memory Chronicles, A Tale of Two Pythons. Please make her welcome.
Good morning. How's everybody doing today? Sufficiently caffeinated for a talk on memory? My name is Kavya, and today I'm here to talk about the memory use in Python, specifically why and how different flavors of Python, different implementations, have vastly different memory profiles. So first things first, what do I mean by different flavors? Some of that functionality doesn't make sense for, and it's unsuitable for these constrained systems. Examples are metaclasses, multiprocessing. It has minimal multi-threading support, but these are things that it just doesn't need, and it would be a bad idea to implement. All right, so CPython and MicroPython are the two Python implementations we're going to talk about today. So the question is, why did I pick these two? Well, it turns out they're actually fairly similar under the hood with respect to the machinery, with respect to how they operate, right? They're both bytecode interpreters, so the Python source is compiled down to bytecode, and that is what's evaluated. They're both stack-based virtual machines. If you don't know what these words mean, it doesn't matter. The idea is the interpreter works, pushes